The following program is brought to you by Caltech.
Good evening. My name is Harry Gray, and I've been working with this evening's speaker for over 30 years. Sort of seems like 100 years. Nate Lewis came to Caltech in 1973 as a freshman, and he joined my research group shortly thereafter. And after a few months where I sort of advised him, he started advising me. And he's been advising me for since then. He worked in my group on rhodium chemistry as an undergraduate, and we did some work in solar energy conversion, making hydrogen fuel from rhodium in acidic aqueous solutions, and even got in Time magazine and Newsweek. Those were heady days. Nate finished a BS degree and an MS degree at the same time in 1977. He wrote several papers as an undergraduate, and we sent him off to our East Coast branch at MIT for a little seasoning. At an MIT, he worked with another former student of mine, Mark Wrighton, and did a beautiful piece of work. And then he joined the faculty at Stanford University, where he rapidly rose in the ranks, doing wonderful work in science. So wonderful that we convinced him to come back to Caltech in 1988 as professor. And he's been with us ever since. He's now the George Argyros Professor and Professor of Chemistry at Caltech. Nate, as you will see, is a wonderful fellow. He's done really pioneering work in the chemistry and physics of semiconductors and other materials. He's led the way in fabricating useful sensors and solar energy devices. And like myself and many of you in the audience, he's extremely concerned about the future of our planet, especially as it has to do with energy in this century and whether, in fact, we're going to survive this century. He's called his initiative Powering the Planet, and he's leading the way nationally in solar energy research. And at Caltech, his Powering the Planet program has involved many of us in research that we hope will make a difference in the future of energy. And tonight, he's going to give us his views about the future in his talk, which he calls Powering the Planet. Where in the world is our energy going to come from? Ladies and gentlemen, my colleague and my great friend, Nate Lewis.
Sure. You're doing guy. Okay. It's great. Thanks. Thanks very much for coming. People often ask scientists what they think about and keep them awake at night. And I'll tell you what I think about at night. I think about what I believe is the single greatest technological challenge of the 21st century. And that's energy. We can't fix poverty without energy. We can't fix not having enough fresh water without energy. We probably can't fix fighting wars without energy. And we have to decide whether or not we'll be committed to seeing our way through this incredibly important problem. So I'll tell you about this problem. I'll tell you about Where we get our power from now, so those are facts that we can assimilate and set the stage for the future. I'll tell you about what we think the future will bring, the future not that far away, that just like our children we need to be prepared for when they grow up, we need to be prepared right now for what happens when our energy system of our children grow up. And I'll tell you where in the world we can get from the physics of the planet the energy that we need to sustain the lifestyles that we're all so accustomed to, that have made the country the great place that it is today. And then the challenges that will be facing us if we actually choose to face this problem instead of running away from it. People often ask me for my slides, and I'm delighted if you get them. You can get them off of my website, which is just my initials at caltech.edu. And I'm happy to have comments about them later on. We need to talk about units here, and energy is big units. It's the biggest business on the planet. So the normal units that we think about need to be adjusted. Of course, power is the thing that we use as the rate of energy delivery, and a laptop is about 1 watt. A nuclear power plant is a billion watts, 10 to the 9th, a gigawatt. And this picture, time-lapsed of the Earth, of course, all taken at night, shows you the electricity demands, and it also shows you the people that have resources and the people that don't even have lights. And that's a terawatt, a trillion watts. And so we will be talking in units of terawatts. This problem is so big that we need units that are bigger than we normally talk about to even describe it. We also need to think about energy, not power. A joule is the unit of energy, and a joule per sec, I don't know where that second came from, sorry. 1 joule is 1 watt for 1 second. So if you run 1 watt in a battery for 1 second, you've delivered 1 joule worth of energy. And again, we'll be talking in trillions and tens of trillions of joules as to what the planet consumes in a day. In fact, if you take the average over day and night over a year, and you think in terms of the power consumed on average by the planet, we consume about 13 trillion watts, day in, day night, averaged over a year. The United States consumes about 1/4 of the world's energy right now. We consume about 3 trillion watts to power our lifestyles. If you read our national energy report, you'll read this number in an archaic unit, 99 quadrillion British thermal units per year. But if you trust me, I've done the arithmetic, that's 3.3 terawatts. And out of that, I won't talk much about the United States because the problems of energy know no boundaries. In fact, there are important social and geopolitical constraints from which countries we will get our energy resources, and they certainly dominate the short-term political horizon. But we need to think more broadly than that, since we all mine the same resources from the planet on which we live, and so we'll think globally, except in rare instances here. For the fossil energy resources, oil, gas, and coal make up now 85% of the energy that we consume in an average year, and are roughly equal in how much they contribute. Hydroelectricity contributes 0.2 terawatts out of our total of 13. Biomass, and this is not sustainably burnt, this is biomass unsustainably burnt, where we burn down forests at a rate much faster than we can replace them. But we use that wood to heat people's lives and provide them with other energy sources in countries that don't have much other developed capabilities, and that's 1 terawatt. The renewable part of biomass is in this total renewables column, which is 0.2 terawatts. And right now, nuclear, mostly, almost all, for electricity purposes, accounts for 0.8 terawatts. For the people that really know, you'll know that this is more than the electricity we make, in just the same way that this amount of coal is more than the electricity we make from the coal. This is the heat content produced out of all the energy resources, and what we do with it later on As we will see, if we choose to convert this or this into electricity, that's a secondary source of supplying energy. This is the heat content of all the primary sources of energy on the planet. And so we can't talk about solutions to problems if we're talking about just large units of gigawatts, billions of watts. If we're not talking about terawatts, trillions of watts, we're not really substantively contributing to this problem. To see renewables, you need a logarithmic scale to even see their relative contributions. And so if you add up all the biomass, there's roughly equal parts for electricity use and for heat and for ethanol, and they add up to that 1/10 of a terawatt. Wind is 10 to the minus third terawatts out of that 13. Solar photovoltaics we hear a lot about. It's a part in a million of our total energy supply. By most businesses, this is a big business. It's a $7 billion a year business growing at 40% a year, and yet it's a tiny fraction of the biggest business in the world, which is the energy business, part in a million. And then solar thermal, that's heating homes and swimming pools. And then other small players like marines and geothermal and some hydro that's renewable. We need to know another fact as to why this is the case. And we can see in a limited snapshot of this is because renewables are more expensive. This is only part of the story, but an important part. This is the cost, 3-year levelized costs in 2002 on a running average of making electricity from various sources. And the smaller numbers here are the short-run costs. That is, once you've built the plant to add some more coal to the fire, how much does it cost you? Versus the long-run cost of from the beginning of making and building the plant and operating it for its lifetime and amortizing the whole costs. And those are the larger numbers, so they give you the spread. And coal is the cheapest source of electricity, and since it's hard to move around, that's why we keep it in the place we find it typically and shove it into a burner and convert that into electricity. And short-run costs are about 1 cent a kilowatt hour, and long-run costs are 4 cents. Natural gas is a little bit more expensive unless you have environmental regulations that will favor it as cleaner burning. And then oil is more expensive, and we don't use it to make electricity. That would be foolish. We need that as liquid hydrocarbon fuels where the energy density is high to move us around, to allow us to visit the places that we use. Wind in favorable sightings is 5 to 7 cents a kilowatt hour. This is in very favorable sightings and assumes no storage and a free grid to which it is hooked up. So it's not really a fair cost basis compared to these other sources which include all those costs. Nuclear energy is not that cheap. A study by our sister institution, MIT, by John Deutsch and Ernie Moniz has just said, and I'll come back to this later, if you built 1,000 new nuclear power plants out of once-through cycles on that scale, that you would be able to produce electricity for about 6 to 7 cents a kilowatt hour. And solar in favorable sightings now is 25 to 50 cents a kilowatt hour. So one conclusion people often come to here is that if we only get solar down, for instance, or wind a little bit closer, that then we'll be economically able to just support ourselves on renewable energy, and that will be that. But that's not the case. The reason that's not the case is because electricity is high-value energy. We sacrifice 3 joules of coal to make every 1 joule of electricity because that's the efficiency of a coal-fired power plant, roughly only 30%. So it had better cost more than 3 times as much as a premium for us to make electricity when we need that for high-value energy compared to just heating your house where all that you care about is the heat content, and that's why we use natural gas instead of all electricity to heat our homes. And in fact, if we were so lucky to pay a nickel a kilowatt hour, and if you looked at your electricity bills, you know that you won't pay that anymore, but that's what it costs the utilities on average. And a nickel a kilowatt hour, if you do an arithmetic conversion, a kilowatt, 1,000 watts for an hour, is a certain number of joules, and I guarantee you that turns out to be $14 per billion joules. But coal only costs $2 for those same billion joules, and oil costs only a little bit more than that. And so you can see that electricity, which is only 10% in the end of the energy that we use, the rest of it, most of it is used to heat our houses, to run our cars, to make our industries, to make our products, to run our factories, and to make the cars that we use from any power source. Where joules count, they're even lower by another factor of 5 or so than the cheapest electricity source that we have. And so if we needed to power our economy on renewable energy, if I delivered you 5 cents a kilowatt hour electricity, I would be delivering you from that 6 cents nuclear power $500 a month home heating bills. A not very satisfyingly inexpensive solution to the problem. Maybe this will change. So maybe the prices will go up of those fossil energy sources in such a way that we won't feel so bad about paying more for energy. Of course, there will be some economic hurt if that happens. I've added up for you all the proven reserves of all the oil, coal, and gas in the world and divided by our 1998 consumption rate. But I've done something else. I've also added up all the estimated resources, what there is still to be discovered. That's a very important number to also know because discovery does not stop in the year 2002, just like it didn't stop in the year 1998. If you look at the proven reserves for both conventional and unconventional resources and divide it by the 1998, it wouldn't change much in 2000 consumption rate. Depending on whether you add them all in and how you do it, you get between 40 and 80 years worth of proven reserves of oil at our current consumption rate. And between 60 and 160 years of natural gas and 220 years of coal. On the other hand, there are two more important points. One is what the estimated resource base yet to be discovered is. And we estimate that by many independent sources to be between 50 and 150 years of oil, between 200 and 600 years worth of natural gas, and almost 2,000 years worth of coal. Furthermore, you should also realize that 2/3 of the oil that has ever been discovered has been left in the ground, not because we couldn't extract it, but because it was uneconomical to extract it relative to a good Saudi oil field, at which it only costs us $4 a barrel to pull it out of the ground right now. So there's plenty of fossil energy around for a while, and if we run out of oil, and with incredible due respect to my close colleague David Goodstein, who's I'm delighted to say here, and who I hope many of you heard before, it's been the case that we've always had 40 years of proven reserves of oil, almost ever since oil's been discovered. And the reason for that, in part, is because when it costs you $1 million a day to drill a well, if you're a company in business doing that, you drill wells until you have 40 years and then you do something else with that money. And the issue really is, could we convert coal and gas to liquids if we needed to and had enough time to know about it? And the answer is it's already been done. Germany did it on a dime in World War II when denied of oil by the Allies. They ran their whole economy on domestic coal. And so we could do that again if we have enough warning time to avoid severe price spikes of the type that David warned us about. We do have an adequate resource base of very inexpensive energy, and China, for instance, has tremendous supplies of coal. So, in fact, does the United States. Since we have an abundant, inexpensive resource base of fossil energy, the good news is that we have a lot of it around if we choose to exploit it. And so at some level, if we diversify our portfolio, we can satisfy our thirst for oil for quite a long period of time without too much economic pain and keep our lifestyles and those of the other industrialized countries going for quite a while. The corollary to that is that renewables are going to be more expensive and therefore will still stay into this tiny role unless we either get to a technological or cost breakthrough ratio so that they become much less expensive and can compete not just with electricity but with the primary power that runs 90% of our planet. Or there's a game changer that comes in that makes us not want to use all that fossil energy even though it is there for the taking. That's the present. And we're going to venture a little further with a little bit of uncomfortableness. It's hard to make predictions, especially about the future. I think Yogi Berra actually probably didn't say this because he didn't say most of what people think he said. But we'll credit him anyway here with it. Nevertheless, that won't stop me. Another close colleague of mine who I'm working with as we spread this message around the country is Marty Hoffert, who is an energy economist and physicist at NYU. And he's analyzed data from an important study by the Intergovernmental Panel on Climate Change in 1992 that actually has been updated recently in the 2001 report. And it's the important issue that we'll discuss next. Energy is what we need. In fact, the currency of the world isn't the dollar. The currency of the world is that joule, because without those joules, we have no ability to make our products or to heat our houses or to even run our iPods. So we really need that. And in fact, energy is shown analytically to be related to people. People are the ones that consume energy. And here's the last century, and here's what we think maybe the next century will bring. This is year 1990 is the dividing line, since it was when these graphs were first formulated by the IPCC. And my favorite out year is the year 2050, in the middle of the next century, which is, as I promised you earlier, the year that we have to worry about now that our kids are going to grow up in. On the planet, we now have about 6 billion people, and you can pick your favorite number as to where it will be by 2050. This is a logarithmic scale, so it's growing exponentially, and most people believe 9, 10, or 11 billion is the right number. So we'll pick 10 billion just to make a nice round number by then. And people consume energy, and as we have more people, we'll consume more energy unless we do something about that. And in fact, instead of just understanding how much energy we'll consume per person, we need to break that down, because if we all just stayed at home and never drove anywhere and never turned on the heating, we wouldn't consume energy, but we wouldn't make anything. And so we in fact need to have two terms. One is the gross domestic product, how much our economy of the planet makes in productivity, and how that will grow, and then the energy we use to make products. And if you multiply the three together, then you can coherently predict energy, and this is what the President's Council of Economic Advisors uses, and what is used by almost all the countries of the world, the so-called Kaya relationship. So on top of population growth, we will have economic growth. Historically, it's been globally averaged at 1.6% per year. And the IPCC said that we think the future will be about the same as the past. There's no compelling reason for that, but most people believe we can't grow at 5% sustainably. And we probably won't grow at less than 1%, because after all, no country has a policy against economic growth. So we're going to grow some here, and we'll just take 1.6% as a representative number, but nothing I'll tell you about will depend on that critically. And then there's a question of how much energy we use per unit of productivity. And in fact, we've been saving energy per unit of productivity as a planet. Historically, that's been declining at 1% per year. And the IPCC said that we believe we will continue to do that. And in fact, the United States is saving energy at twice the rate of the world. We're saving energy per unit of GDP at 2% per year. Now, of course, we are on a higher base than most of the other countries of the world, not all, but most, per unit of GDP. And so it's easier for us to save because we already spend more out of our account than others do. But it will still take, and in fact, the President has committed to showing the world how to save energy by continuing to save energy at twice the rate of the rest of the world on average. Now, of course, the developing countries are developing and are not saving such energy yet as they grow. And so that's what takes the world average to half of the United States decline of 1% per year. And we hope we can continue to do that. This means, this is an incredibly aggressive target, that in 50 years we will use half as much energy per person on average on the planet as we use now. And everything we can think of to do in terms of end-use energy efficiency and fuel cells and energy-efficient zero-energy buildings and energy-efficient cars that go 70 to 80 miles a gallon, and everything involved will be needed in order to meet that target. And so we will build in incredibly aggressive energy conservation into this already. So we're going to assume that from this day forward, we all strive to doing that. And then we'll see what the outcome is. If we multiply the number of people by the GDP, by the energy consumed per unit of GDP, we get energy. To show you how aggressive that demand conservation is, here's the United States already right now in energy per GDP. Here are some other countries. And here's where we anticipate the global average will be in 50 years. So that means the United States, to stay on this track, will have to use 5 times less energy per person than we use now. Not 50% less, 5 times less. So 100-mile-a-gallon cars would barely make the goal just for transportation. And we will build that into the model. So we'll assume we all get onto that path starting today, and that we make that goal. This is in principle technically possible. A study by the Swiss have said if we throw every energy efficiency technology imaginable at end use, could we get to a civilization where everybody's mean average was 2 kilowatts? And the answer is technically yes, although it depends on several key levers, not only the United States, but of course on India and China, which weight heavily in the average because they're growing and they have a lot of people. Assuming that that's the case, and that we impose incredibly aggressive demand reduction, twice as many people need twice as much energy because economic growth is offset basically by that demand reduction, and we would need 28 terawatts to supply our thirst for power in the year 2050. And that should be no problem because after all, we could follow that curve just by drilling more and just by mining more coal, and if need be, converting that coal into oil. ExxonMobil is spending $10 billion right now converting plants into ones that can convert natural gas into liquid form and oil for exactly this purpose, to protect our ability to have liquid fuels if in case we start to peak elsewhere. So we could do this. And then there's a problem. The problem is, what if we got what we wished for and we did? Here's the amount of carbon that would be produced into the atmosphere in the form of CO2 if we actually do satisfy our thirst from energy from that fossil energy resource. This is the amount of carbon produced per unit of energy from many energy sources, and this is the global average on the planet for the last century. And you can see that wood is the least energy efficient source, of course. It's not very useful to heat yourself remote from wood, and so it takes a lot of carbon emitted into the atmosphere when you burn wood to heat your cave. On the other hand, you do a little bit better, not too much better, but a little bit better by burning coal. You do better by burning oil, and that's because coal is all carbon, and when you burn it, you get all carbon dioxide. There's no option. Natural gas is CH4, methane, and when you burn that, you get one carbon as CO2 and you get 2 water molecules as H2O. And so you get more energy out and less carbon because you also get 2 waters. And then oil is in between its chemical stoichiometry. It's on average 1 carbon and 2 hydrogens in between 1 to 4 and 0. And so these 3 things can be done nothing about. They are a consequence of the chemical formulas of burning these different fossil energy resources. You can't change them. The average carbon intensity averaged over the whole mix on the planet in 1990 was there. The IPCC said, along with that very aggressive, in my personal opinion, demand reduction scenario, that we will be equally aggressive at decarbonizing the mix as we have done naturally for the last 50 years over the next 50 years. And that we will naturally, under business as usual, continue to follow the curve, which brings us to 2050 to an average carbon intensity below that of the least carbon-intensive fossil energy source. To get there, it's obvious from simple arithmetic, the only way to get the average below that of the least carbon-intensive source is to have something that contributes no carbon into the average at all, or you can't make the arithmetic work. Furthermore, to the extent that we don't burn pure natural gas in our entire energy economy on the planet, but equal parts oil, coal, and gas, or maybe even weight it more heavily to coal, we will need even more zero carbon energy to get the average down to here. But we will assume this will happen naturally also. Since we know energy demand per year under aggressive conservation, and we also know the amount of carbon produced per unit of energy burnt over that year, we can simply do arithmetic to predict how much carbon will be in the atmosphere under these optimistic scenarios by the time our kids grow up. And that curve is this top curve. These other curves are the amount of CO2 needed in the atmosphere to stabilize at certain atmospheric concentrations, and the numbers correspond to the concentrations that we would stabilize at. The carbon dioxide concentration in the atmosphere before humans started to emit much fossil fuel was 270 parts per million, and it was stable for many thousands of years at that level. This level would bring us to more than triple that by the mid-21st century and would not stabilize that even into the foreseeable future, even with that carbon average below that of a pure natural gas economy and with incredibly aggressive demand reductions in energy. If you wanted to stabilize at 350 parts per million, the entire planet can't burn another ounce of carbon from the year 2050 onwards. This is pure arithmetic. We know this to be a fact because we know the amount of carbon that will appear in the atmosphere, and we know the fraction of that that will stay. So there is no doubt about this. If you want to stabilize at other numbers, you need more zero in order to meet demand, in order to bring the atmospheric concentration levels down. This we know is going to be a fact. What we do not know, as a scientific fact, is what the impacts of raising the carbon dioxide levels in that atmosphere will be on our planet. We do know more than that. We know from ice core data over the last 500,000 years what the temperatures have been and what the atmospheric carbon dioxide levels have been. This graph shows you the atmospheric carbon dioxide levels have been between 200 parts per million and 300 parts per million, but never higher over that 500,000 years. They've shown oscillations in the carbon dioxide level that track essentially precisely the temperature changes. We know that changes between 200 and 300 are correlated with, but not necessarily causes of, temperature swings that have caused ice ages on our planet repeatedly. We know that we are on track with aggressive conservation measures and with aggressive decarbonization to produce triple the pre-anthropogenic levels. We are already, from the data on Mauna Kea by Charlie Keeling, observing CO2 climbing at a level that has never been seen on the planet in the last 500,000 years. And we are on track with aggressive conservation efforts and decarbonization efforts to still be far short of stabilizing that, even at double the pre-anthropogenic, the pre-human levels. We don't know what a safe level will be. There are computer models that sometimes predict that 550 doubling might resemble borderline the planet that we live on. Other such models predict that the Arctic will melt its sea ice as it's doing, that perhaps the Gulf Stream will shift direction and Great Britain with the latitude of Labrador will have the climate of Labrador. And there are other such issues. The answer is we don't know. The other answer is that we won't know from a computer model because we would need 100 years or more worth of precise data to predict this small an effect. And so if you wait for the scientists to run an analytical model to predict what the effects of this will be, we will simply do the experiment first. And the question is, how lucky do we feel? If you feel lucky, you stay on the track we are and you let it happen and you hope things will work out okay. The other important point is that unlike the ozone, the lifetime of carbon dioxide in the atmosphere, there is no natural destruction mechanism. It has to exchange with the oceans in order to be absorbed by the oceans to go away. And even if we decided we didn't like what we saw, the lifetime is such that we would be stuck with it for several hundred years because nobody has a mechanism of extracting the 600 trillion pounds of carbon dioxide that will be there by then. Climate change is not just about global warming, it's about the climate changing. I didn't write these predictions this year, although statistically it might be an anomaly. These are some of the robust predictions. More of the rainfall should occur in downpours. It's not like we might not have seen that this last winter. Corals should bleach because they're sensitive to the pHs of the ocean. 20% of the corals are already bleached, and the predictions are because they're so sensitive to the pH as we add the CO2 that most, if not all of them, will be bleached within that 2050 time period. Glaciers should retreat. They're retreating all over the world. Sea ice should shrink. It is shrinking. Sea level should rise. If the Greenland ice sheet melts, it will rise 20 feet. And that will have problems for many of the major cities on the planet. Wildfires should increase as we get more extremes in humidity, and storm and flood damages should be much larger. Hurricanes should be more. Here's a picture of Glacier National Park in 1910. Here's a picture of Glacier National Park now. It soon will be a non-glacier national park. Glaciers all over the world are melting. We cannot prove unequivocally that the carbon dioxide is the cause of this. We can just wait and watch and see what happens. Here's a picture of Greenland in the ice sheets 50 years ago, and here's a picture of Greenland now. Here's a picture of corals, 20% of which around the planet now look like that. Under the business as usual scenario, the arithmetic says that you need 10 terawatts of carbon-free power to run our economy in 2050, even under that aggressive demand reduction. And if you want to stabilize the atmospheric carbon dioxide levels, you need even more. You need 15 or 20 terawatts. What this says is that if you choose to go on a different path and are serious about not doing the experiment, we need to find a way to supply as much power from carbon-free energy in 45 years as we supply now in the biggest business in the world, the fossil energy business, today combined. Nothing less is a serious effort at stabilizing these atmospheric CO2 concentrations. You shouldn't think that you can just conserve your way out of this. Aggressive conservation was built in. It can buy us time, but that's all it can buy us. If we were fortunate enough to keep energy demand constant in the face of population growth and economic growth, because the lifetime is on the order of 50 to 100 years, the atmosphere is still adding it all up. And that means that even if we halved our energy right now and kept it constant, we would buy ourselves, instead of to 2050, all the way to 2070. Marty Hoffert says these underscore the pitfalls of wait and see. How in the world, if we had a technology today, could we develop it on such a scale by 2050? And we don't have such a technology today. And we probably need a Manhattan Project or an Apollo space program to have a chance. My conclusions are a little different. We don't need such a Manhattan Project or an Apollo space program if we want to stay on course, because the lowest cost option is to simply pull our fossil energy out of the ground the way we continue to do it now. And unless we're willing to spend more money to buy insurance against being lucky, then we won't do anything else. So now I'll tell you what you would have to do if you wanted to actually seriously get 10 terawatts of carbon-free power, because the scale of the number in itself sets the scale of what the solutions are allowed on our planet. There are only 3 sources that scale. One of them is nuclear power. The second one I'll talk about is so-called carbon sequestration, the driver behind the hydrogen economy, and the third are renewables. And I'll first turn to nuclear power, because in fact, if we needed to get 10 terawatts of carbon-free power, right now it is the only technology that we have that could scale, that could provide us with that option. And so we should not rule it out, because it's a question of what's the worst of the 2 options. But we need to consider what we are voting for, because if we don't do anything else, then this is what we are deploying if we choose to solve the problem. I am not personally anti or pro-nuclear or any other energy source, but these are the numbers. Nuclear power plants, as you saw on the first slide, produce about 1 billion watts, a gigawatt, and that's of electricity, and they're built to about the limits of their structural integrity at about that 1 gigawatt, where we believe they're still safe. And so we would have to build, to get to 10 terawatts, 10,000 such 1 gigawatt nuclear reactors. That's 1 reactor somewhere in the world every other day, continuously for the next 50 years. I've been giving this talk for 4 years in one form or another, and we should have by this time built more nuclear reactors to stay on track than the world has ever built collectively to date. So we're behind schedule. It turns out that you would deplete all the terrestrial resource base of uranium at that scale in 10 years. You could get it from seawater, but it's dilute. And so you would need the equivalent of on the order of 10 Niagara Fallses spanning the Earth's oceans to mine it all, but we could get it for 700 years. Or there is another option, of course, and that is to go to breeder reactors, which would involve plutonium. There are, of course, other issues with that. We should actually credit North Korea and Iran for doing their part for mitigating global climate change. But it's the only option we now have. And so if we decide to go down this alternate path, we need to take it seriously. The next issue is carbon sequestration. And that is still be addicted to the fossil fuel habit, but just bury it somewhere in what I like to call a Dennis the Menace cleaning job, when your mom's going to inspect the room and you put all your clothes in the closet and hope that she doesn't look there. So we'll put all our carbon dioxide in the closet somewhere on the planet and hope that it doesn't come back to haunt us. And there are only three places we could think about putting it. One is in the deep oceans, and there's enough capacity there to absorb those billions of tons, the 6 billion tons of carbon dioxide that we emit each year for quite a long time, except that it's an acid, and it will change the pH of the oceans quite rapidly, and that will destroy the ecosystems and propagate. And so that's largely now technically not considered to be a viable option. There's a second option, which is to put it in the oil and gas fields, but there's not enough capacity there. And the third option is to put them in the underground aquifers. There's enough capacity for 100 years to do that, and the idea is you'd have a coal-fired power plant, and as you burnt the electricity, the CO2 would come out of the stack and you would just bury it down there. Here's where all the underground aquifers are in the United States. There's 100 years worth of capacity. Here's where all the power plants are. And you can see that some of them are co-located. Others would have to be built anew or relocated. And in fact, this is the driver behind the hydrogen economy, because if you're going to bury your carbon dioxide, then you can't pump carbon around to people. You have to supply them energy that's carbon-free, and we would make hydrogen out of that, assuming that this works. Because there's no guarantee that these underground aquifers won't leak. And if the carbon dioxide that we've made is Perrier under the ground, which, by the way, costs more than oil, and if we decided to sell the Perrier, we could fix our balance of trade problems quite quickly. Nevertheless, if we decide to leave it under there and it leaks at 1% per year, then after 100 years, the flux is the same as we started with, so that's not a technical solution. And in fact, it can't leak at 0.1% global average. To calibrate you from drilling, there are already over 1.5 million holes in the crust just drilled in Texas for oil exploration. So we will have to plug up some holes, and it's never been technically proven that sequestration will work at scale at a 0.1% leak rate for 1,000 years. And we will have to do that in the next 20 years in order to have confidence that we will be able to sequester it so that it doesn't come back to bite us 50 or 100 years down the road. We need a lot of subsurface science and technology to do that, and you should not assume that it's a given that we can run the hydrogen economy out of burying our waste this way. It is something we should absolutely work on technically, but it's hardly a done deal. And the third, then, option suite is just get renewables. Don't make the carbon in the first place. And the 6 common renewables that we talk about often are hydroelectric, geothermal, ocean tides, winds, biomass, and solar. And I'll go through each of these and tell you what the limits are of the physics of our planet as they dictate where we could get such large amounts of power. Hydroelectricity is considered a model renewable energy resource. It's relatively benign. It's often commonly used. When you build a dam in China, you only displace 1 million people, but all energy sources have their problems, and that's a minor one. But if you add up all the kinetic energy in all the rivers, lakes, and streams on the planet, it's worth 4.6 terawatts in total. Now, you can't get hydroelectricity by damping up every little swamp, and so where you can actually technically get it is only 1.5 terawatts worth. And you actually can't technically get it everywhere, because although we could technically dam up the Hudson River, there are smaller complications, like the Yankees won't have anywhere to play and George Steinbrenner won't like that. So where it's economically feasible is only 0.9 terawatts, and our installed capacity is 0.6. We only make 0.3 because Niagara Falls doesn't go at full steam all year long. And so there's, in fact, hardly any room to grow because hydroelectricity is relatively cheap. We've done it pretty much where we can do it on the planet. What about geothermal energy? In some places, nature is kind to us, and hot water just comes right up in the version of steam to the surface of the earth, and we can just run a turbine off of it and make electricity. But in most places, you have to drill down on the order of 10,000 meters, 10 kilometers, to get to a 200-degree centigrade temperature gradient, and you would pump in cold water, and the hot, dry rock would heat it up, and out would come hot water, and then you would run a machine to get electricity out of it that way. You can see maps like this that show you what the hydroelectric resource is in places like Yellowstone, where, of course, it's a little geothermally active and less than in other places. But let's add it all up. All you need to know is if you ask someone like David Stevenson here, in any geophysics textbook, what the average geothermal flux is at the surface of the Earth. We know the temperature of the Earth core, we know the diameter of the Earth, we know its conductivity, and so we know how much heat is escaping. That's worth 57 milliwatts per square meter. And if you multiply by all the areas of all the continents on the planet, it's worth 11 terawatts. And so you'd have to cover all the continent with 100% efficient heat engines if you wanted to get that. In addition, a good geothermal well pair is only worth 5 megawatts because it's a phase change, not a chemical change. And you cool it off after something like 5 years because the hot rocks get cooled off by that cold water and you have to drill new wells. Here's a 20 terawatt line. Here's all the energy and all the ocean currents and all the tides and in all the waves added up. They're not 10% of what we'd need. Here's a map of wind. You often see this map of if we covered North Dakota with windmills at 5% spacing and excluded where there are cities and forests, and then we got some in Texas and Oklahoma, we would get 100% of something. The Wind Energy Lobby says 100% of the energy, but that's not what NREL said from the map when they created it. They said we would get 100% of the nation's electricity, which is on the order of 10% of our total energy. So we'd get 10% of our energy if we did it everywhere. Now, in fact, that's an overestimate because the map was never intended to be used this way. Because, in fact, if you put windmills everywhere in North Dakota, I know as a windsurfer, when I get behind my colleague Paul Dimatakis's beautiful sailboat, I lose a lot of wind. And there wouldn't be any wind left by the time you got to this point in North Dakota if you had windmills everywhere there. So it's an overestimate of what the actual resource base is. How much needs some calculation. In fact, probably the practical estimate is 2 terawatts globally of wind resource if we did it everywhere in all the high wind speed areas. Why couldn't we go to lower wind speed areas? Because the energy in the wind goes like the cube of the velocity of the wind. It's an easy exercise to show that I give to my freshmen at Caltech in their energy sciences class here. So you lose economically tremendously as you go to lower wind speed areas, which is why we only see them out in Altamont Pass and in the San Gorgonio Pass, and even then it looks like half of them aren't even working most of the time. What about biomass? Plants actually are not optimal energy conversion machines. Nature didn't optimize them for that purpose. Plants are green and look pretty. If they wanted to absorb more sunlight, they would be black. And in fact, if you wanted to get 3 terawatts, you can read the numbers. You would need 31% of the total land area on Earth covered. But a more instructive way to calculate this, and this is what the fastest growing plants that we now know, switchgrass, is to take all the land that we now could grow crops on and to subtract off all the land we currently grow crops to feed ourselves. And then to take half again as much, because after all, we're going to have twice as many people, and we'll assume we have agricultural efficiency improvements. And so we'll subtract half again as much, and we'll take all the rest, and we'll plant it with the fastest growing crops that we know of, and make the assumption that the gross output of the farm is equal to the net, that is, no energy is input into the farm, which is, of course, not the case. In fact, you should not confuse energy policy and energy politics in the Midwest of the United States It's barely break even to make ethanol from corn. You put as much energy into the farm as you get out from the ethanol. We do that for energy politics. We don't do that for energy policy. But we will assume we get it all out here. And if you did it everywhere, if you had enough fresh water to water all those crops, you would get maybe 5 to 7 terawatts. Biomass should be taken seriously, provided that we're willing to genetically modify and engineer plants to grow faster and be more productive photosynthetically and maybe black instead of green, and to have what we might lovingly call Franken plants to power us, or bacteria to do this, and these should be absolutely taken seriously if we are to try to help exploit advances in biotechnology to help get an energy source on the planet that doesn't involve further releases of carbon. And there's the last one, which is why biomass has a hope. Here's the solar constant, this 10 to the 5th terawatts. That's the amount of sunlight that hits the Earth every day. This is corrected for the amount of clouds that scatter 30% of that. The energy hitting the Earth in 1 hour of sunlight is more than all the energy consumed on the planet in a year of fossil energy. Practical siting, this is just a factual statement. Practical siting says you could get 600 terawatts. Photosynthesis right now produces, in detailed balance, 90 terawatts worth of energy for us that is balanced by respiration. Why don't we use solar heating for this purpose? Because there's a day-night mismatch. We need the energy when it's cold from the sun. We have to store it, and we need it in the winter, and we get it in the summer. And it's low-grade energy, it's heat, and that costs a lot of entropy, is what it's called, to store that energy, so it's relatively expensive. On the other hand, if we could do it in the way we could store it usefully, this is the amount of area you would need to cover to supply all the United States electricity and total energy forever. The glass is either half filled or half emptied. This is 10 times bigger than the area of everybody's roof. It's comparable to the nation's highway system. But in the 3 years and some that I've given this talk, I have never met anybody that actually lived there. You would never do it this way. You would distribute it all. The lights are out, so I'm not going to take a poll because I'm afraid I'll lose my track record here. But if someone does actually ever live there in this audience, you could come up afterwards, and I'm happy to talk to you about what life is like there. This is a representative mid-latitude, and it's day-night averaged, and you wouldn't just do it there, but I didn't pick a hot spot in Arizona. It gives you a feeling for how big you would have to be. Here's 6 3-terawatt boxes. And you basically get to choose whether or not you want to do that, still one of the biggest projects we could ever embark on, or whether or not you want to build a nuclear power plant every other day for the next 50 years. There are 3 ways we know how to store solar energy. One is nature shows us the way with plants and bacteria, and it shows us another answer that we don't know how to do effectively yet. It stores that for the nighttime because it makes chemical fuel. But unfortunately, it does it with low efficiency, and so we need large areas unless we co-opt the system, which is an important line of research. The other is the one you're probably more familiar with, photovoltaics that make solar electricity. And they work much more efficiently. They can be 20% efficient. In fact, in some cases, I'm of course always proud to say that in the family, my wife has many of the world records for the most efficient solar cells from her research in this area. On the other hand, we can afford that on space missions where it's cost per pound that matters, not cost per watt. And so on Earth, these give us far too expensive solutions right now, and they don't store that electricity. And if we don't store it, we will never be able to use it for primary power, because after all, the sun doesn't shine at night every night. And so we particularly work on a hybrid between those, which I won't talk much about in this context. I will need another talk to tell you about the details of my particular work here, where we co-opt systems like this to work like this and make chemical fuels, because in an integrated way, that would solve the storage problem in a way that photovoltaics by themselves do not. This is an important graph because it tells you the cost that such a system has to be. Because after all, if the sun's going to shine for 30 years, we know from the physics of the sunlight how much energy will hit a square meter. And if we get 10% of that to, say, useful energy as electricity, then we know for 30 years how many total electricity electrons we'll produce. And if it costs you $300 a square meter to put up that cell, then you'd better sell me that electricity for at least what you paid to make it over 30 years, or you'll lose money. And so you can see all solar cell technologies are right here at about 10% efficiency and cost about $300 per square meter. And by the time you're done calculating that, that means you have to sell it at 35 cents a kilowatt hour to $1 a kilowatt hour or more, or you lose money. And that's the problem. In fact, you can also see that since we have to go down by a factor of 50 to compete with primary power, that you can't just do this by improving the efficiency, because you can't improve a 10% efficiency by a factor of 50 and make it work. You have to lower the cost. The cost has to be somewhere in here, on the order of something like $10 a square meter. To give you a feeling for what that cost means, the cost of paint at Home Depot is $1 a square meter. And so this can cost you about 10 times more than painting your house, but not much more than that. So we can't have expensive single crystals that we've grown up with to make photovoltaic cells. We have to have really cheap particles, but we have to find a way to make those cheap particles fooled at the surfaces in the atoms that aren't connected to the other atoms in the bulk of those crystals. Fool them into thinking they're in the bulk and make this stuff work like that stuff, because this works well, but it costs too much to make the light come in and last in the excited states that make electricity all the way through to get to the backside. The problem right now here is that when these carriers hit the edges, they lose their energy because it knows it's at the edge of one of these crystals, but there's no reason it has to know. There's no law of physics that says these atoms at the surface have to be different than those in the crystalline material, just that we as chemists haven't found a way to glue them together yet in a way just like making paint. So that's what part of my group is working on, in conjunction also with, in a different modality, part of Harry Gray's group. If you use organic materials, they can be very cheap, but just that those carriers can't last to make it all the way, and so maybe we shouldn't make them go all the way back. Maybe we should only make them go sideways, where we can collect them in little fingers. And those things we like to call interpenetrating networks, where you could go out of this standard cost per watt basis, and we're working on that approach also, again in one modality, in conjunction with Harry Atwater's group, and another in conjunction with the other Harry Gray's group. And so our goal here is to, I wish I had a penny for every time someone now used this phrase, although no one's got there yet, but we coined it, is to make solar paint, because it can't cost much more than that. And we got to find a way to make these particles work where it's literally like painting your house, not like putting panels on the roof that someone installs in these precious glass slides, because that's going to cost way too much. Let me return to this cost curve for one other point, because the cost has to include the fact that we know there's no sun at night. And if we don't include storage in the system, then all the photovoltaic cells on all the roofs are only going to power us between 10 and 4 when the sun shines, and then we're still in trouble. So we better find a way to store it. The cheapest way to store electricity is not in batteries, because batteries don't last for the full 30 years. They can't charge and discharge for that long a period of time, and so you end up having to replace the batteries every 2 or 3 years. And the cost of the batteries would far exceed the cost of the cells that you put up, and so it's uneconomical. The cheapest way now technologically is to pump water uphill instead of pumping it out of a dam. Just fill the dam the other way with the electricity, reverse hydro. That works well in Switzerland. They have a very shallow country in that sense, and in addition, they do it for summer-winter variations, but we need to buffer day-night variations. And that would require a very thin dam with lots of pumps, and turns out not to be so economical. And there's, of course, one other way, and that way is to remember that nature solved this problem. It makes chemical fuels. You'll see this on the DOE website, where we're going to somehow take all of our resources and put them into a machine and make a fuel that is promoted to be hydrogen as the answer to the problem. In fact, this doesn't recognize the differential values of different fuels. If we ever had enough biomass, which right now we can't have enough of, to actually use, we would not convert it to hydrogen, an inferior fuel. We would thank our lucky stars and make biodiesel out of it and run our cars off of it for the liquids that it would be worth as a liquid gold, and we would declare victory and go home. We would never convert that to an inferior fuel, hydrogen. We would never take electricity, high-value energy, and convert it to an inferior, lower-value form either. We need to find a way to make that fuel directly to complement the things that we know how to do. Furthermore, if you could make hydrogen, the first places you would use it are in fixed sites. And if you wanted to ruin the hydrogen economy, you would wait until you worked it for transportation first. Here's how we make hydrogen now from the sunlight. You don't need to see more than this. You take these poor parabolic arrays and you focus the sunlight onto that poor little solar cell, and you take the electricity out of that solar cell and you run it through half the world's electrolyzer of platinum, and you fill up that little tank with hydrogen. This obviously is incredibly expensive. So we have a scheme. That scheme is to borrow from what nature does, to take a membrane, just like the leaf does or a bacteria does, to separate the reactants and the products, to evolve hydrogen on one side of the membrane and oxygen on the other side of the membrane, and to take those paint particles that we've oriented and to separate the electricity so that it generates our fuel with no wires outside and bypasses all the complications of making electricity and then feeding it in to those expensive catalysts. This is the opposite of what you would do if you wanted to make a fuel cell work effectively, because this takes those same fuels and runs them in reverse to make electricity, and we're running it the other way with light as the input source instead of electricity as the output source. We don't know how to do this yet. That's why we need help from Jonas Peters, a colleague of mine who is helping make the catalysts along with Harry Gray in our group. Because now we have structures of how the biological system works. Because there are enzymes in biology called hydrogenases that do evolve hydrogen very effectively and that don't use noble metals. They use what nature gave us, iron. And they're not poisoned by sulfur and carbon monoxide like the platinum metals that the fuel cell companies are struggling with to avoid the expense of and the durability of. And so we're trying to borrow what nature teaches us in a lesson and pull it out into this integrated system to try to make fuel as well as integrate that with the storage. We can do this now, we just can't do it very effectively and very inexpensively. We actually can make hydrogen from water and sunlight, but the materials that we know how to use right now that work well, unfortunately only absorb in the ultraviolet. So they would work well on the moon, but we need to solve our problems on the Earth first here. And so we're exploring new materials to try to sustain this electrolysis in a cost-effective way. Finally, let me summarize. I think it's pretty clear that we are going to need additional energy. Even if in our wildest dreams we could keep it constant in the face of growing economies like China and India and more people wanting into the society that we don't want to keep them out of, because otherwise we're saying that they must stay in poverty while only we get to enjoy it, which doesn't seem appropriate or fair. We're going to need more energy to power those people on the planet, even if we conserve a lot. And even if we do that, the case for significant and probably daunting carbon-free energy seems either plausible or imperative, depending on how lucky you want to feel. So what are the scientific challenges? I've often asked if I'm in an elevator with the president, what do I tell him? And the answer is pretty simple: cheap solar fuel. Because if it isn't cheap, we can't afford to do this. This isn't like sending a man to the moon. This is like trying to send a man to the moon when Southwest Airlines is already there and handing out peanuts. We already have a cheap energy source that runs our economies, and we have to compete with that. All right? It needs to come, at least in part, from the only energy source that is capable of supplying much more energy than we need. You could piece together a 10 terawatt contribution with some from nuclear and some from wind and some from everything else, and might get to the 10 terawatt target if you stressed all of those resources to near their limits, and that's probably not a good idea, because anytime you stress the resources to their limits, you end up with cost and technology issues, and it's not clear we have enough resources to develop all of those technologies at once anyway. But if we don't make fuel, then we have no way of delivering it to the end use, and so we better not forget that the sun doesn't shine at nighttime and find a way to deliver that to the end user in a way that can power our economy. So we need cheap solar fuel, is what we should be working on in addition to sequestration and in addition to thinking about building those 10,000 new nuclear power plants. I haven't mentioned policy much in this talk on purpose because I've tried to keep it technical, and I'll only allude to it here in the end. So there are 4 securities that are important. One is energy security, the next is national security, the third is environmental security, and the fourth is economic security, and we can all prioritize these in different orders depending on our personal preferences, but they're all there and they're all important. We'd like to get all 4 at once. If we do build those nuclear power plants, it's not clear that we'll get all 4, maybe only 2 out of the 4. If we go to coal and sequestration doesn't work, we might get energy security and economic security. We might have to fight for our resources, so we might not get national security because wars have been fought over energy in the past in civilization, and there's no reason to think they won't be fought again in the future. And we might have a carbon problem if sequestration doesn't work. If you were to go to solar or renewables, you would satisfy all 4 of those, and it's the only option in our portfolio that could, and so I think we ought to do that. The other policy question is this a project that it would be nice if we succeeded, like in some level, curing terrible diseases, but if we don't, the world is the same, or is this a project where it's simply the case that we can't afford to fail? And if that's the case, then we have to decide whether or not we're going to be committed to actually doing it on a scale that will allow the people involved to give it a fair chance. When we spend more money at 10 minutes buying oil at the pump than we spend funding solar energy in a year, it's not going to get there. When the Department of Energy's Office of Science's budget is smaller than the NIH's budget increase, then it's not going to get there. I'm not the only person saying this. Rick Smalley, a Nobel laureate, is saying this. Steve Chu is trying to redirect the entire Lawrence Berkeley Laboratory, a Nobel laureate, toward this exact same goal and has testified in Congress on this. I'm going there in 2 months to do the exact same thing. Harry Gray, of course, agrees with this idea and is working hard on it as well. And the question is whether or not we'll have the courage to actually face the problem in the 20 to 30 year window where we will, in principle, if we work at it, and I'm optimistic that if we do work at it, we might well try to solve it, but if we don't work on it, then we will simply do the biggest experiment that humans have ever done, and we're just going to have to hope that we turn out okay. So with that, I want to thank you for coming, and now you know what keeps me up at night, and I would be happy to answer questions.